lab right here. Like Ben, I have about 40 slides, but unlike Ben, I only have 15 minutes. So I'm going to take you through a kind of a whirlwind tour of our efforts to build a scalable community detection algorithm for large biological sequences. But before we get there, I want to start with comparative genomics. People will probably be shocked to learn that comparative genomics is all about comparing genomics data. And in order to compare genomics data, we have to be able to know what genes or genomic sequences we can compare and which ones we can't. So being able to run any kind of analysis like building gene trees, any of these kinds of things, depends on having an answer to this question of which genes are the same across organisms. If we have some sort of gene family, then we could reconstruct gene trees for them. But we don't want to build gene trees for genes that are not the same, and we want to build gene trees from all the genes that are the same. So this is commonly referred to as like orthology detection or finding clusters of orthologous genes. And the process by which we do that is not super simple. It typically involves a long pipeline that begins by taking our pairs of genes, here referred to as these boxes, and quantifying sequence similarity in some way. This can be BLAST, it can be whatever your favorite flavor of BLAST is. And if we do this for all pairs of genes that we have, we end up with this sort of sequence similarity network. Here we have genes as nodes, so these colored boxes, and the edges between them are how similar the genes are. Here I'm showing basically every edge in our graph, but if we weight our edges by how similar the sequences are, a lot of the edges get stronger, a lot of them get weaker, and you end up with kind of this smaller, sparser network. You can see here that we have two kind of cleared groups. There's the 4 on the left and there's the 4 on the right, but there's sort of these spurious edges. Maybe I can get a laser pointer, that'd be cool, in the middle that are still there. So this is the point of a community detection algorithm. It takes one of these networks that is mostly split, and it identifies communities of related nodes from the network. In this case, finding these groups of related genes that we can use for, come on slides, that we can use for downstream analyses like building gene trees, comparative genomics, whatever your favorite kind of later step stages are. So for the purpose of this talk, I'm going to talk specifically about this step of community detection on sequence similarity networks. And just to be perfectly clear on what we're doing here, we're starting with a graph of some kind. It has nodes, it has edges. Our nodes are genes, the edges are how similar the genes are. And the point of these algorithms is to essentially label the nodes such that we have these groups of genes that are related to each other and other groups that are different. You can think of it sort of like a coloring. Hopefully my colors work on this slides. They're okay. We want to color everything that's the same color, and different genes, different colors. So this is not a simple problem. There's a lot of algorithms that do this. They have been introduced over the years. They all optimize for different things, produce different sorts of communities depending on your priorities and what you're interested in doing. And I'm saying different priorities because it's not super straightforward to tell what we should be doing in a specific scenario. So if I pull up some random gene network, this is a bunch of genes, sequence similarity, I can run community detection algorithms on them. Here's 4 different ones, and here are lots of different communities identified, lots of colors. They're relatively similar in some ways, so I can point out some key characteristics here, like, this kind of blob here tends to be all grouped in the same color. This kind of blob here tends to be grouped in the same color. But there's also some disagreement among the algorithms. So if we look at this top orange group of nodes, each algorithm differs in how many communities it thinks are present. Some it says 1, some says 2, all the way up to 4. The question is which one is right? So we want to start with this problem of figuring out what the best starting point algorithm specifically for the use case of sequence similarity networks is. We took a lot of existing algorithms that work for this for general purpose networks, because computer scientists love networks. They love to do this kind of thing. They haven't investigated them specifically for sequence similarity networks. So prior efforts to benchmark have focused kind of on graphs like this in the top left and less on graphs like this. They're much different. This graph is very uniform in how its edges are distributed. Everything tends to be connected to everything. But in reality, when we look at sequence similarity networks, they tend to have different properties. We tend to have networks that have sort of a power law distribution in how many edges each node has. They don't have uniform weights. They will have some stronger weights or some weaker ones. And critically, we'll have weak edges collapse to zero. This is just a product of how the data is set up. If we run blast searches between very different genes, we're more likely to get no similarity than to get like very low degrees of similarity. So anything close to zero ends up just becoming zero. We built a synthetic benchmark because we don't know the real truth and real data using these sorts of modified benchmark networks. We built about 1 million of them, ran a bunch of algorithms. I'm not going to spend a lot of time on the results because I don't have a lot of time in total. But the key takeaways I want to just highlight here are the best performing algorithms we see are one called label propagation, one called Louvain, and the one that's most robust to these missing edges kind of scenarios is one called MCL. This roughly correlates with what people are already using in the literature. So if you are familiar with these and you're using them, nice job. Okay, now the focus of this talk isn't really most accurate algorithm. There's another problem that I haven't talked about yet, and it relates to kind of the modern age of genomics. So we have lots of genomes. Each genome has thousands, if not tens of thousands of genes in it. And when we build these sequence similarity networks, each additional gene we add leads to one extra edge per genome in our set. What does that mean? It means that as we add more and more genomes, the size of our network is going to grow with the square of the number of genomes we have. And it's no secret that the amount of genomic data we have is kind of increasing exponentially. So you can think of these networks as growing exponentially squared, a lot, basically. Algorithm development in computer science in general is really a trade-off between accuracy, speed, and computational resources. So we're always balancing these three constraints. And even if we kind of have identified these most accurate algorithms, another concern with the modern kind of genomic data is how long does it take them to run and how much are we paying for it? So this is kind of a best case scenario. We build very sparse graphs to just highlight the lower bound for how long it would take these algorithms to run. These are the top performers from before, label propagation, MCL, and Louvain, along with a faster variant of label propagation that was recently introduced. And these are going to take for 50,000 genomes on the order of weeks to years, which is not ideally what we would want to be happening. I know what you're saying. There's one algorithm that only takes 6 hours. That's terrific. But again, it's all about trade-offs, and things that run faster, when we look at their memory consumption, end up taking significantly more amounts of RAM. So 6 hours, but we're paying for it by using 300 gigs of RAM to process 50,000 genomes. 50,000 genomes sounds like a lot, but we're moving towards kind of an era where we have thousands and thousands of genomes. If you go into RNA-seq data, you could even have more genes that you're analyzing. So all these algorithms scale linearly in terms of memory. So the bigger your graph gets, the more memory that's required. And this is kind of an issue because when we look at the cost of memory over the years, in the past decade, we haven't really seen a change in how much RAM costs. Typically the approach is just buy bigger computers. Not everyone really has access to high performance compute. And if we're thinking of linear scaling, I mean, 50,000 genomes, 300 gigs. If we move it to double that, we're at 600. If we're going to the scale of maybe millions of genomes, we could be asking for hundreds of terabytes of RAM to process them. Not super sustainable in the long term. Okay, so what do we do? There is sort of an alternative. Depending on how familiar you are with old computer science, we can go back to disk space. Disk space costs orders of magnitude less than it costs to be in RAM. And the cost of solid state drives is decreasing sort of exponentially, at least over the past decade. So this is maybe an option. So this is the groundwork for the algorithm we are trying to develop. We want something that has good runtime scaling, something that has good memory scaling, and that is as accurate as everything else. So we kind of want to have our cake and eat it too. It goes huge and it does well. This led us to the introduction of an algorithm we're calling ExoLabel. It has two pieces, Exo and Label. The label component comes from the algorithm it uses. It's fast label propagation. This is the algorithm from before that performed well in accuracy, took about 6 hours projected time to run, and consumed around 300 gigs of memory. On top of that, it incorporates two big innovations. The first of these is that as much as we can, we're storing stuff on disk space like your hard drive and not in the RAM of your computer, which means we can go much bigger. It means that our RAM footprint should be roughly constant, and we can leverage the significantly cheaper hard drive space. Secondly, we introduce another kind of piece we took from a different algorithm, MCL, called an inflation operator, which as we continue to process our network, we refine the communities that we're identifying. We make weak edges weaker, strong edges stronger. If you want to see what it looks like over time, it kind of makes the graph coalesce towards its strongest edges. And this probably seems like a kind of random thing to do. I'm happy to talk more about why we're doing this. I don't have the time now. So the takeaway is this allows us to guarantee that it will converge in log linear time with basically no impact on accuracy. So we can run just as well, but it takes less time than alternatives. So synthetic benchmarking accuracy is basically the same. I'm going to skip those results to focus on the cool ones. Sorry. If you're interested, so first starting with RAM usage, I just showed this before. These were the previous algorithms that we were analyzing. Scalable on the same results takes about, you can see it in green at the bottom if it's showing up. Come on. There it is. About 100 megs of RAM rather than hundreds of gigabytes. Now, obviously, that data has to be somewhere. We're not just making computation work out of magic. It does come at the cost of using about 90 gigs of disk space. But when you look at trade-offs, like I think there's probably very few people in this room that have a 300 gigabyte RAM computer. But 90 gigs of disk and 100 megabytes of RAM is something that would run on this phone. So probably most phones here. So the RAM requirements are constant. The disk space requirements are linear in the size of your network. So scaling's not terrible. But again, people are probably thinking, okay, why doesn't everyone do this? It's probably very slow if we're going to disk space. That's why everyone uses RAM. It's fast, disk is slow. It turns out because of the previous optimizations we incorporated, our runtimes aren't crazy. So we're looking at about best case 2.5 days, which is better than alternatives that don't use this space. So fast and low footprint, and the scalability is log linear with the size of the network. I think I'm running out of time. So quickly, we looked at some real data. I mean, simulations are nice, but real data is always better. This is preliminary results. We took about 50 prokaryotic genomes. We're going to scale it to much bigger in the near future. They're from RefSeq, and in short, it's about 150,000 nodes and 850-ish edges from very diverse phyla. They're there. Ask me about them later. We don't know the ground truth communities in this network, but we can look at how similar it is to algorithms we know work. So we looked at first a heat map of how similar the communities from Scalable are relative to alternatives. So darker is more similar, lighter is less similar. I know the words are pretty small, but the takeaway is there's 4 algorithms it's most similar to. Those ones are exactly the ones that performed well in our synthetic benchmark. So it produces communities that are similar to label propagation and to MCL under its default parameters. I can show statistics on the communities we're actually getting. I'm going to skim over them. The takeaways are some algorithms make big communities, but not a lot of them. Some of them make small communities and a ton of them. We end up being closer to the more smaller communities side. Whether or not that's good kind of depends on what you're analyzing. But I can showcase more definitively what that looks like looking at some real data. So come on. There it is. Okay, so this is a piece of that network. Obviously, I can't show an 150,000 node network. Sorry, thank you, on one slide. But these are the different communities we've identified. I said there are some algorithms that build big communities, but not a lot of them. One example is Louvain. It looks like this. And the problem with that is we end up with things like this, where we have sort of 2 distinct communities that are weakly connected, and we're joining them together into larger communities, not really what we want to see. The alternative, come on, PowerPoint's not cooperating with me here. The alternative is if we make a lot of really small communities, that works up to a certain point, but then we end up with sort of a problem where we start over-splitting communities. So like you can see here on the right, we have this very densely connected community that the algorithm is trying to sub-split into multiple sub-communities that don't make a ton of sense. If you can't, that's like yellow and blue. Okay, so Xlabel comes in right in the middle at what, at least from an eye inspection, looks like a nice medium spot of good delineation of communities, but not over splitting. And compared to alternatives that people use, it basically does exactly the same. I'm going to just skip through this. So in summary, this enables scalable community detection on sequence similarity networks. It should work on other biological networks. We just haven't taken it there yet. It uses about 100 megs of RAM. Actually, since I wrote this, it's down to about 60 megs. And the runtime is log linear, so it scales well. And the accuracy is basically equivalent to other comparable methods, but with less requirements. So it's distributed within the SynExtend package. It's available on R. If you have questions, please talk to me later. I have no time for questions for sure, so sorry. Here's my lab.